hope you can see stuff that I write in real time. For example,
Yeah, I think I can.
what number did I just write?
An 8.
Okay, all right.
Sweet.
So, acceleration. Boy, they have a tricky way of introducing you to calculus without calling it calculus.
Yeah, seriously. Seriously.
That's what this stuff is.
Hmm.
It's actually a little easier in calculus.
Is it?
But yeah, because there's just formulas you use. But
Gotcha.
it's the
Just,
concept that's kind of tough.
yeah, you just have to know which like formula to use for each question.
Well, acceleration is the change in velocity.
Okay.
Okay?
Uh-huh.
So, what is our change in velocity when we slow from 45 miles per hour to 25 miles per hour?
Would you just do 45 minus 25,
Uh-huh. And,
which
well, not quite.
divided by 8?
No, well, almost.
Almost.
Are we slowing or speeding up?
Slowing.
So it's negative 20.
Yeah.
In other words, it's negative 20 miles per hour
Hmm.
divided by 8 seconds.
Okay.
If we simplify that, what do we get? 10 fourths, 5 halves minus 5 halves. And notice
Hmm.
what the units come out to be. You get
Hmm.
miles per hour per second
Hmm.
is the units of acceleration.
Okay.
That means every single second you're slowing down by 2.5 miles per hour.
Hmm.
8 seconds to slow down to that.
Okay. Cool.
Okay. So basically that's what we're going to do on all of these is we're going to
Okay.
find the rate of change of the speed. If every
Okay.
question is on acceleration, then
Hmm.
we want to know what the change in acceleration is.
Okay.
Hold on a second. Let me read number 2.
Sure.
Car coming down the hill
Mhm.
takes only 3.5 seconds to arrive at the bottom of the hill and is traveling at 50 miles per hour after accelerating at a rate of 6.6 miles per hour per second. Find the car's initial speed at the top of the hill.
Mhm.
All right, so here's where we want to start.
Okay.
It accelerated at that
Mhm.
for 3.5 seconds.
Mhm.
So what was its starting speed? If its final speed is 50 miles per hour, and for 3.5 seconds it's been accelerating, work backwards. What was its initial speed?
Uh, let's see here. Um, we don't know that.
Well, we're going to calculate it.
Yeah.
We take its acceleration rate
Uh.
and multiply it by 3.5 seconds.
Mhm.
Notice the seconds cancel, and we're going to come
Right.
up with what its starting miles per hour were.
Mhm.
So what's 6.6 times 3.5?
Oh, let me see. I got a calculator here. 23.1.
All right. Now, I want to make sure that you see that this is the same as problem number 1,
Mhm.
only they give you different variables.
Yeah.
In other words, they told us in problem number 1 that we went from 45 to 25 in 8 seconds.
Mhm.
Calculate acceleration.
Mhm.
Well, that's final speed minus initial speed divided by 8.
Uh-huh.
Well, this second problem They give us the acceleration and how many seconds it's been accelerating and the final speed. So it's still the final speed minus the initial speed, which we'll call x, divided by the number of seconds, 3.5. And that's going to be the acceleration rate, which is a positive 6.6. So that's our equation that applies to number 2, and it also applied to number 1. Notice number 1 was 25 minus 45, the end speed minus the beginning, divided by 8. That's where we got our minus 5 halves.
Okay.
Well, it's the same equation for number 2. We take our ending speed, 50, minus our beginning speed, which we don't know. But we're going to solve for it and set it equal to our acceleration rate. And when we do all that, we came up with 23.1 miles per hour. And it would certainly need to be a rate less than 50 miles an hour because the guy's going downhill, he's accelerating. So if his speed at the bottom of the hill is 50 miles per hour, his speed at the top has to be less. Okay, so acceleration, this gets a little tricky actually. I don't know if they're going to get into it here or not, but acceleration appears to be when you're slowing down it's negative and when you're speeding up it's positive.
Yeah, that's basically it.
Well,
that's what they've been.
Not totally true in calculus, but going to be true for all of these problems, I suspect.
Okay.
Calculus direction matters. So number 3, what's the final speed of a roller coaster that begins a steep descent at 1 millisecond or 1 meter per second? That's its
meter per
starting speed. Accelerates at 3.2 meters per second squared. Notice that what 3.2 meters per second means meters per second per second. It's the same as writing it like this, meters per second per second.
Yeah.
Well, in the first 2 problems, we were doing miles per hour per second. So when everything's in seconds, then it's meters per second squared.
Okay.
Okay. All right. So it's the easiest way to do number 3. Let's not always rely on that formula. Let's think about it.
Sure.
So it's accelerating at this rate for that amount of time. What's its speed going to be?
Wouldn't you just multiply it?
Yeah. But make sure you add it to its beginning speed.
Right.
In other words, this is how much speed it's going to pick up. What is that? Multiply those together.
Let's see here. 3.2 times 6.5.
Yeah.
20.8.
And notice what the units are. In other words, this seconds canceled with that exponent.
Right.
Our units are meters per second. That's the amount of speed we gain during our acceleration for 6.5 seconds. Well, what was our starting speed?
1.0 meters per second.
So what's our final speed going to be?
21.8 meters per second.
You got it.
Okay.
Okay. Now we could use the basic formula on all these problems, but I don't think that's the best way to learn it here. I honestly think that it's better if you think about it conceptually and figure out things like, what's its beginning speed, what's its ending speed, how long is it accelerating for that at that acceleration rate. All right, let's think about this one.
Yeah.
Okay. This is the one question that does not involve acceleration.
Yeah.
In other words, what formula is going to apply when we're talking about distance, rate? Notice what we're seeing here. Distance, rate, and change in speed. Well, what's the average speed? So we need the equation what's the anagram I give it? It relates D, R, and T.
Right. So it'd be distance is equal to 3.r times 10 to the third.
Hold on. Give me the general formula.
Oh, distance is equal to r divided by t.
No.
Is it just RT?
What word do I use to always make you remember this?
Distance is equal to
dirt.
Dirt. Yeah, I knew that. Yeah. Yep.
Well, if you knew that, then it's not ever r divided by t. It's always r times t.
Okay.
And the only thing that we're substituting is an equal sign for the I. Otherwise, it's spelled dirt. And the reason I use that is because you can't get it wrong.
No, you can't.
I'm going to write that D equals R over T. That's not dirt. Dirt has to be times, okay? So that's the equation we're going to use.
Okay.
And we travel this distance at that speed.
Mm-hmm. He said, but I digress. Ethan.
How long did we take?
Sorry.
Now let me write it out a little bit. We've got 10 to the third is that.
Mm-hmm.
So we got that distance, 3,000 meters. So plug it in.
Yeah, 3,000 is equal to, would be 30 meters per second.
Times time.
Yeah.
So what's time going to be? How long did it take us to travel that 3,000 meters?
We don't know that, do we?
Yeah, we can solve it. Here's the equation. What's time going to be?
Let's see. So it would just be, okay, wait, 3,000.
That for t.
You would just subtract 30 from both sides, right?
Well,
wait, I'm lost.
If I say 3,000
divided by
30t, how do you solve for t?
Divide by t, or 30t.
Divide by 30, not t.
Yeah.
In other words, you're trying to isolate t. So you're trying to get rid of anything that's associated with it. And right now it's being multiplied by 30, so you got to divide everything by 30.
So right. So t is equal to 100.
100 seconds. So it took 100 seconds to go that distance.
Yeah.
Now it enters a town, and instantaneously, which is actually not possible, but given that this is not a calculus course, it instantly slows to 12 meters per second for this distance. Well, how much time does that take if we use the D equals RT? Over here on the left, D equals RT. They're giving us the speed that it slowed to and the distance. So what's D?
So 6,300. We're looking at 6, right?
No, we're looking at 4.
Oh, we're doing 4. My bad.
We're doing the second part of 4.
Okay.
In other words, this train is going 30 meters per second for 3,000 meters, and then it instantaneously slows down to 12 meters per second for 800 meters. So how many seconds did it go through town? That's what we have to figure out.
Okay, so it'd be 8,000 is equal to
800.
800. Yeah, my bad. Is equal to 30 meters per second times
Hold
t.
on. It's
Or
12.
no, it would be yeah.
Remember, this is the second part of the trip.
Yeah, I didn't see the 12 there. Yeah.
So
So you
how
would just
long
divide
did
them.
it take to go through town? Town is 800 meters across, and it slowed all the way down to 12 meters per second. So let's figure out how many seconds it took to get through town.
66.6. All right, 66.7.
Now, they want to know the average speed.
Mm-hmm.
Well, back to our d equals rt again.
Uh-huh.
d equals rt, only in this case, the distance, since they're talking about average, is going to be that first 3,000 meters plus the next 800. So 3,800 goes in for d.
Mm-hmm.
R is what we're going to calculate, the average speed, and the time is the 100 seconds plus the 66.6 seconds.
Mm-hmm.
So it's 166.6 is my time. Now my average speed is 3,800 divided by 166.6. What do you get?
Okay, let me do that. $57.05.
No, I don't think so.
Is this
3,800 divided
38?
by 166.6.
Yeah, dude, 22.8. My bad. I guess it didn't put in the 1. That was weird.
2.8?
22.8.
22.8. Okay. So that's its average speed on the two journeys. It's very important to think about this in this way. In other words, we did not come up with the average by taking the average of 30 meters per second and 12 meters per second. That would have given us an average of 21 meters per second.
Right.
That's not the way you do these problems.
No.
What you have to do is figure out the total amount of time you took on the first part, add it to the total amount of time you took going through town.
Okay.
Now you know the total amount of time, and you know the total distance is the two distances added together.
Right.
So when you solve for R, you're solving for the average speed from the beginning of this journey, the beginning of the 3,000 meters, to the end of it.
Okay.
The end of 3,000 meters plus another 800 meters going through a small town. So this was not an acceleration problem. That's why those directions said not everything is an acceleration problem.
Right.
All right, let's do more acceleration. Number 5.
Yeah.
I'm not going to have time to do all of these.
Oh, it's okay. Yeah.
We should be able to do number 5.
Yeah. Okay. So would you do 80 meters per second times 2.5 plus 15 meters per second?
Here they're talking about acceleration.
Right.
Remember what acceleration is. It's the change in speeds. So you take the ending speed minus the beginning speed, always. So 80 minus 15,
right.
That's 65, but only divided by some number of seconds, and this whole thing is equal to 2.5 meters per second squared, which is units associated with acceleration. So I take my change in speed, which is positive 65.
Okay.
I divide it by the number of seconds that we were uniformly accelerating. They don't give us that. That's what the question is. How much time will it take? Well, remember how we did all these problems. We took our ending speed minus our beginning speed divided by the number of seconds that it's doing that. That gives you acceleration. So now that I have this formula here, is all I have to do is solve it. 65 divided by x equals 2.5. How do you solve that for x?
Cross multiply.
Okay, so what do you get?
So in the end, you just divide 65 by 2.5.
Okay, and that's going to be your answer.
Okay.
Now, you don't always have to carry forth all of the units. They can make it kind of complicated. In other words, if I look at this, that's actually 65 miles per hour divided by x seconds. Excuse me, that's not miles per hour. That's 65 meters per second.
Yeah.
So that's MPS. Divided by seconds gives you meters per second squared. So the units, you can be sure, will work out.
Right.
The only thing you kind of have to know is whether you're accelerating or decelerating. If you're decelerating, your acceleration is negative. But if you're going from a slower speed to a faster speed, you're accelerating. As anybody that drives knows.
Yeah, for sure.
Do you drive yet, Dylan?
What's that?
Do you drive yet? Do you have your license?
I do have my license, yeah.
Yeah, so you know the feeling of acceleration in a car.
Definitely, yeah.
Fortunately, most high school kids do, which is kind of a bad thing because it makes them go too fast most of the time.
Agreed.
And it's fun to accelerate at a high rate of speed. That's why people spend all this money to get a Tesla that'll go from 0 to 60 in 4 seconds.
Those things are fast, yeah.
I know.
You wouldn't think, since it's all electric, you wouldn't think it'd be that fast. But
well, it doesn't have a big, heavy engine. It's a light car, so that's why it can accelerate that fast. It doesn't have an engine that needs to be in there. Of course, it's got a lot of batteries, but all the batteries don't weigh as much as an engine does. And a transmission and everything else that a regular car has to have that a Tesla doesn't. Anyway, Dylan, I got a 6:30 tonight, so I'm gonna have to let you go. Even if we got through half of these, but I think you get the idea.
Yeah, no worries. What?
Speed minus the beginning speed divided by the number of seconds that took place equals the acceleration. Just always use that formula, and you can go back and solve all of these, except for number 4. Number 4 is a dirt problem.
Right.
It's not an acceleration problem. It's a dirt problem. All right. Dylan, talk to you next time.
Okay, hold on. My dad wanted to say something real fast. What? Hurry. Oh, yeah, my dad has a new address for billing. I'll just text it to you since you have it at 6:30.
Couldn't you do that?
Yeah, I can text you.
Thank you.
Yep, definitely.
Okay. I don't send anything by mail anyway, so everything goes to his email. I presume that hasn't changed.
No, it hasn't.
Okay.
So we're good.
All right. Talk to you later.
Sounds good. Thanks, Mr. Cowan.
Bye-bye.
Bye-bye.